Assalamu alaikum, everyone. Hello and welcome to a new episode of GDA Conversation Series, brought to you by the Gulf Downstream Association, which is a non-profit association founded by Saudi Aramco, Bahrain Petroleum Company, Kuwait Petroleum International, Kuwait National Petroleum Company, and Abu Dhabi National Oil Company, for sharing knowledge and experience among all downstream players. My name is Munif Al-Shamiri. I'm Refinery Energy Coordinator at Bahrain Petroleum Company. I'm also playing the role of chairperson of the GDA Energy Technical Committee. It's my pleasure to moderate today's webinar on the topic of understanding and eliminating the risk of waterhammer. Waterhammering is a phenomenon that can occur in any pipe system, in a piping system, where valves are used to control flow of liquid or steam. The shock waves caused by sudden close of the valve or sudden shut off of a pump may propagate at the speed of sound, as water is incompressible. If repetition of this phenomenon is not addressed in a timely manner, it can cause a series of damage to the asset and even cause a cross traffic. I'm honored to introduce Mr. James Bandle, who will share his experience on this topic in today's webinar. Mr. James Bandle is the global subject matter expert for oil, gas, and petrochemicals processing with Spirax Sarco. James started his career with Foster Weller, and his experience includes the process design of refineries unit, ethanol glycol plants, and LNG plants, as well as steam and condensate system. James has worked with many downstream improvement projects in his career, with JCC and globally. At Spirax, James is the design authority for associated steam condensate and thermal energy solution. James holds a master's degree in chemical engineering and is a chartered engineer. Today, we are also joined by many subject matter experts from various GDA technical committees for deep dive discussion with James. Now, let me, with you, welcome Mr. James. James, floor is yours.
Thank you very much. Thank you for your introduction. Okay, so welcome everybody to my webinar on understanding Waterhammer. As you said, my introduction, my name is James Bandle. I'm a chartered process engineer. And at Spirax Sarco, my role is global oil, gas, petrochemical processing subject matter expert and also project manager. So the intent of my webinar today is to raise awareness of the causes and potential damages of waterhammer and to really highlight what can be done to minimise and control this phenomenon. So I'll be talking through what waterhammer actually is, how it can occur, what the mechanisms are that cause it, and where it can occur. Looking at the possible causes, risks, consequences of waterhammering when it does occur, and then really focusing on how that can be avoided through good design, through good operating, and good maintenance practices. So as far as Sarco, we always like to start off all of our meetings with a safety moment to keep safety central to everything we do. So this safety moment I have is obviously waterhammer related. And about 10, 15 years ago now, 20 years ago now, there was a period of 2 weeks at Grangemouth Refinery and Petrochemical Complex, which is in Scotland. And there were 3 different events that occurred. First of all, there was a power distribution failure. And about a week later, there was an MP steam main rupture. And then the last event, just shortly after that, was a fluidized catalytic cracker unit fire. Now, each of these events had the potential to cause fatal injury to personnel, but also have quite serious environmental impacts. Although in these cases, no serious injury did occur, and there was only a short-term impact on the environment. But focusing on the MP steam main rupture case, It was an 18-bar medium pressure steam main. It was located very near the south site boundary, and there's a public road on this site that runs through the middle of the plant. And that was where it ruptured. It resulted in a significant loss of MP steam directly to atmosphere. But more importantly, it damaged fencing and equipment adjacent to the road. And debris and steam was blown across the road for a period of about an hour until the leak was isolated. The leak also had quite a loud noise. It sounded like a jet engine taking off, which caused disruption to the local area, breached environmental regulations from a noise perspective. And there was also a member of the public walking their dog about 300 meters away when the incident occurred, and they sustained injuries from falling over in the shock of the situation. And the site itself was impacted because for about an hour or 2 hours, the site steam supply distribution network was compromised, which meant process units that consumed the steam were also then compromised and needed to shut down or be brought down in terms of performance. So it's quite a big site-wide impact. The investigation into the cause found that actually the Waterhammer incident was linked to the site-wide power distribution failure that had happened the previous week. And what happened was that excess amounts of water during the power failure event were sent to drain, and it also combined that with the fact that there was no electrical power for drainage pumps to operate. And this led to flooding of culverts, service tunnels, which carried the MP steam mains around the plant and under this public road. So because they were flooded, it was necessary to send people into these culverts to assess any damage to pipework and the pipework supports. And to do that safely, a steam trap, which was located at a low point in the section of pipework in the culverts, was closed to allow for the safety inspection. And this steam trap was subsequently not reopened when operations restarted. And this prevented removal of the condensate from this section of the system. And so over time, liquid condensate built up in this bit of pipework. And eventually, there was a quantity of steam or some steam bubbles that were trapped between the hot condensate and a closed isolation valve local to this piping culvert. And eventually, the steam bubble collapsed and resulted in what we call condensation-induced waterhammer, which led to these pressure waves, gross overpressure of the pipeline, and catastrophic failure of the steam line. So the investigations into circumstances surrounding all three of these incidents at the Grangebath complex were investigated by the UK Health and Safety Executive, and they considered their findings to be issues which the industry as a whole could learn from, try and assist the major accident industry in reducing the probability of major incidents occurring in the future, and also reducing the severity of incidents when they do occur. And the key message to take home really from this were that major accident industry should be aware and ensure that knowledge from previous incidents are learnt and passed within their organisation and incorporated into current safety management systems. The operators should have increased focus on major accident prevention in order to ensure that business risk is controlled and to ensure there's effective governance, and that the control of major accident hazards, COMA safety regime, is a living process. It's not just an ad hoc sort of periodic process. It's a living process that should be used as a day-to-day management tool in assisting process safety management. So I hope that going through this webinar will inform, provide information to help understand how Waterhammer and what causes Waterhammer is an ongoing thing, and that needs to be built into all elements of design, operation, maintenance to prevent these incidents occurring in the future. So to start with then, what is Waterhammer? So the important thing to note is that Waterhammer is a symptom. It's not the problem itself. And the term Waterhammer is used to refer to notable effects which are actually caused by a few quite different phenomena. And Waterhammer is so called because it's usually observed with the banging sounds of pipes bouncing around in their supports or hitting onto other surrounding equipment. Waterhammer is not limited to industrial settings. It can commonly be seen at home in domestic settings, caused by something as simple as quickly closing a tap. And what happens is you can see at home quite visually that pipes or hoses in the garden can move. And this is due to the pressure waves in the water. And they might strike floor joists or walls and create that banging noise. But due to the short pipework lengths and hoses involved and the small flow rates in houses, Waterhammer in the home is rarely more than an irritation. Industrially, however, Waterhammer can be much more than a minor irritation. And in general, Waterhammer effects occur when the velocity of fluid suddenly change, or the flow becomes unsteady or transient. And this can be across the system as a whole, or it can be very localized points. But because it occurs due to changes in flow, the mechanisms that cause Waterhammer are always present to some degree in the systems, because changes in pressure, changes in fluid properties are required for maintaining and controlling process conditions. And therefore, any fluid flow, any process control actions create pressure changes. That's what they do. That's how they control things. And all of these pressure changes result in forces being applied within the process, within the fluids, and then from there transferred to the containing equipment. Normally these forces are small, such that their presence isn't noticed, and it's well within the equipment design parameters and the tolerance of the mechanical design of the piping equipment. But if the rate of change of pressure is high enough, the forces generated can have noticeable and really significant effects that can be seen. And this can be seen as sort of violently moving pipework that's jumping and bouncing around, and it can be high enough even to burst pipe walls open. In the following slides, I'll describe how it occurs, what the different mechanisms are, how it manifests, and then consequently to that, how to prevent and guard against it. So as I said, Waterhammer being the symptom, not the problem itself, the important thing is to identify the correct mechanism that's involved in particular circumstances in order to then understand how severe the incident may be, or the potential may be, and therefore how to avoid it through good design operating practices. But without identifying the correct mechanism, the solutions that are applied might not be correct. So the three different mechanisms that I talked through are steam flow driven Waterhammer, condensation induced Waterhammer, and hydraulic shock or surge, as it's sometimes known. So the first one then, steam flow driven Waterhammer. There are a couple of ways in which this can be caused, it can occur. So the first one is accumulation of condensate in steam piping, which results in the formation of waves or slugs that form by the action of the steam flowing over the top of the condensate. And this picks up the surface of the liquid into waves, and then they can build into slugs. And that's much the same way that ocean waves are created with the wind blowing over the surface of the sea. The second way it can form is that liquid pockets can collect at low points that aren't properly drained, or form with pipework sags over time, supports don't keep it nice and level. And then that slug, once it builds up to a certain volume, can get pushed out ahead of the steam to form a slug of liquid that carries off down the pipework. And the issue occurs when these slugs or waves are pushed along the pipe by the following steam, and then when they get to a restriction or a bend in the piping, the momentum of that liquid wave, that slug, is transferred into the equipment, applying a large force at that location. And the worst case for this is that liquid slug completely fills the whole cross section of the pipe, and it's therefore driven along at the full steam velocity, which could be up to sort of 40 meters per second, so very fast. And the effects are likely to be greater, obviously where there are high steam velocities, but also where you've got longer straight lengths of pipe, which allow formation and acceleration development of larger liquid slugs. So this mechanism usually, I say usually, is a result of accumulation of condensate over time, and therefore the effects tend to build up over time too. So it might start off as some minor knockings, some minor movements of pipework, but if it's not, if no intervention happens and the condensate still carries to build up, it will get greater and greater and greater until the forces become too much to be contained. It's not always the case though. You can get slugs or the effects of slugs coming out of nowhere. So particularly if things collecting a low point, it's not known that liquid's collecting the low point, and then suddenly, the steam velocity changes and it pushes a slug out ahead of it. That can be a sort of sudden, quite severe event from nowhere. So that's the first mechanism that causes Waterhammer. The second one is condensation-induced Waterhammer. So this phenomenon can occur in a number of ways, but the first one, steam is allowed to enter into a system that contains condensate, so steam bubbles, steam injection into that system. The next one is the reverse of that, so water is put into a system that contains steam, particularly if the water is subcooled. And the third one then is vapor pockets again, so this can exist at high points under certain operating conditions, particularly in shutdown, as the diagram shows here. If the pump stops, the liquid in the system will settle out to the level in the tank. and leave a vapor pocket at the high point that's caused by kind of low pressure being formed as the liquid drops down. And what happens in this form of Waterhammer is that you get rapid condensation of the vapor, either caused by sudden cooling of that vapor as it comes in contact with a cold liquid, or in the case of the sort of diagram with a high point leg, starting with the pump increases the pressure in the system, and that pressure causes the vapor to condense and collapse. So the vapor condenses, as I said, then the volume it takes up dramatically reduces because the density of liquid is much less than the density of the vapor. So the bubble collapses, the pocket collapses, and you get a sudden rush of liquid to fill that void. And that sudden inrush of liquid to fill the void, be it a big section of piping or just a small steam bubble, is called an implosion. And the forces that generates are very high, as kind of these, the liquid faces hit each other. So it creates very high pressure pulses in the system, and those pressure pulses then spread out, radiate out, and impact on equipment and can impart very high forces on the equipment. So it's kind of similar in practice to, well, similar in some ways to a sort of cavitation in pump, where you get those implosions of very tiny bubbles on the impeller. And this is a similar thing. It can be very small bubbles locally, but it also, as I said, could be much bigger pockets. And when they collapse, the forces are much higher. This kind of water hammer can occur very suddenly from seemingly nowhere. You could hear a sharp cracking sound if it's sort of small amounts of steam being injected into a full condensate line. On the other hand, it could be a big vapor pocket that just sits there quite happily, not changing for a long period, and a sudden change in temperature, a sudden change in pressure causes very sudden collapse of that pocket, and then the effects are felt very suddenly. So before we move on to the third mechanism for water hammer, I'll point out that the steam flow induced water hammer and the condensation induced water hammer can combine to create water hammer together. So it can start off in the same way that steam flow driven water hammer does, where you get the flow of vapor, the flow of steam over the top of the condensate layer in the pipe, and this causes waves to pick up on the surface that could form into slugs. And when they form into slugs that completely fill the cross-section layer of the pipework, you end up getting pockets of vapor trapped between the peaks between the slugs, the peaks of the waves and the slugs in the pipework. And then as these get compressed as the wave moves down the line, or you get further loss of heat from the pipe wall, again, these vapor pockets can collapse. And then you get the condensate-induced water hammer kicking in, where you get the implosion of that vapor bubble, the inrush of liquid to fill that void, and then the high pressure pulses and force on equipment that result from that. So this can happen in steam lines as well, but obviously you do need a certain amount of liquid to be able to kind of fill the cross-section over the pipework to create these pockets. The third mechanism for water hammer then is hydraulic shock or surge, as it's commonly referred to. And this is a very different mechanism to the previous two. It's not caused by slugs traveling in a sort of two-phase line. It's not caused by condensation of vapor in a two-phase line. It's caused by sudden changes in the bulk fluid velocity of liquid bulk systems. So it's a very different mechanism, as I said. And its cause is because liquids, although we tend to treat them from a design perspective as incompressible, actually liquids are very slightly compressible. And as a result of a sudden restriction to flow, so closing a valve or a pump suddenly stopping, the whole column of liquid does not just suddenly stop instantly. What happens is the kinetic energy that's in that flowing column of liquid is transferred into the fluid by compression of that liquid. And this results in pressure shock waves being generated. And these pressure shock waves can travel at speeds, usually close to the speed of sound along the pipework, and conveying that change of pressure. And the greater the rate of change of liquid velocity, and the greater the mass of liquid that's being accelerated, so the length of the pipeline, the length of the column of liquid, the higher the resultant peak pressures. And this particularly steps up in terms of the peak pressures that are generated when the piping length exceeds the pressure wave length. You then get a compound length, because these pressure shock waves can bounce backwards and forwards from obstacles and restrictions in the pipework. And one of the biggest overpressures or the biggest overpressure scenarios typically occur on the back of the restriction. So here what happens is you've got the forward momentum of liquid flowing away from the sudden restriction, from the closed valve, for example. And this causes a big drop of pressure, a vacuum to evolve on the back of this restriction. And then as the pressure wave bounces back towards that restriction, it causes that vapor pocket, that vacuum to collapse. So again, you get a combination of this pressure surge bounding back, compounded with this vapor bubble collapse as the shock wave hits it. So in this scenario, you can generate very high peak pressures from the liquid surge alone, the pressure wave bouncing back, but potentially much higher pressures even during this vapor collapse on the back of the valve as well. And these pressure waves can quite easily significantly exceed piping design conditions. So the actual peak pressures can exceed flange ratings, to cause loss of containment from the pipework. But because of these very high pressure waves that can bounce up and down the system, they impart very high sort of moment forces on the pipework. So again, when it hits bends and fittings or supports, it can quite easily be torn and broken and damaged by these pressure waves bounce up and down. I think it's fair to say that Waterhammer, any of these mechanisms can be pretty severe, but perhaps the most severe is caused by this hydraulic surge, hydraulic shock mechanism. Having explained the different mechanisms causing Waterhammer phenomena, it should be apparent, I think, that Waterhammer effects can occur almost anywhere around a plant. It's not just confined to steam and condensate systems. But as the effects are more likely to be noticeable in systems which have higher fluid velocities, have greater inventories, and have greater potential for mixing of steam, both steam and condensates, the following systems are typically the most common systems in which Waterhammer is experienced. You can see it is generally commonly around the steam and condensate systems. So steam flow water-driven hammer, obviously very much on steam distribution pipework, but also on two-phase condensate return lines. And I've noted here as well that you can see it on single-phase condensate return lines, where it's operating it should operate at saturation pressure, and therefore if you have high pressure drop in the line, flow meters, restriction valves, that kind of thing, you'll get flashing through that system, and therefore it turns into a two-phase condensate stream, and you can get hammer therefore in that line. The condensate-induced water hammer can occur anywhere you can get the flow, steam flow-driven water hammer. But in addition to that, so through the steam and condensate return lines, you can also get it's common to see it close to steam consumers, where you've got steam coming in as a potential for steam breakthrough. If the steam usage control and the condensate return control, the control valves or steam traps is not maintained properly, you get the breakthrough into the condensate system. So it's quite common to see induced water hammer occurring there. And particularly around these areas during startup and shutdown, it's quite common when systems are not up to temperature. You've got a lot more condensate around the system than you'd expect to have normally. You haven't got the normal flow rates. The normal control systems aren't functioning normally, so you're relying on manual intervention, bypass valves, bypass lines, that kind of thing to start up the systems. You're introducing temperature, steam, where you haven't got anything already, which you're building up. That's a real common situation to see condensate-induced water hammer. And of course, that tends to be located around the steam used as the heat exchangers, for example. The third type of water hammer, so the condensate surge shock, being a very different mechanism. Obviously, that can occur in different locations. As I said, you need liquid-filled lines for this to happen. And as I said, as the peak pressures are worse for long transfer lines, you tend to get it on the long interconnecting lines between different parts of the plant. So a common one is product transfer down to storage across 500 meters, a kilometer, 2-3 kilometers of pipework out to the tanks farm or to ports and jetties. But you can get it on the condensate return systems. It's not unknown to be there, where you're transferring condensate from various processing units back to a centralized steam plant. Again, the pipe length there can be long, and therefore it can be prone to condensate to hydraulic surge water hammer. So before looking at the mitigation measures, just to highlight what the potential consequences and risks of water hammer is, and I covered some of this already in the safety moments. But we've seen that clearly can have quite significant adverse safety, environmental, and commercial consequences. And there's real potential for equipment damage, resulting in loss of containment, personnel injuries or fatalities, and environmental damage that comes with the loss of containment. But obviously, it's not just limited to that. If equipment is damaged, or even if pipework is knocked around, it can have quite significant consequential production losses, as pipework has to be isolated, equipment has to be tested and checked to make sure it's safe for continued use, and all of this on the steam system can disrupt the steam supply to process units. And without that, production has to be scaled back or even stopped, which obviously is an expensive and time-consuming business. And perhaps more importantly, perhaps in the long term, is potential for reputational damage. As I mentioned in the safety moment, the Waterhammer and the rupture of the MP steam main at the Grangemouth complex caused debris and steam to be sprayed across a public road. There was injury to a member of the public on the road, and also the noise was heard for hundreds of meters all around, very high levels. And all that can add over time to that loss of reputation. And these events do need to be investigated by sort of government's health and safety agencies. It's all on public record. So again, that can have reputational losses too. The good news, though, is that the Waterhammer and the likelihood and severity of it can be greatly reduced through appropriate system design, and then following that through into operating and maintenance activities. They're really important into maintaining a safe plant, a safe environment, and to properly reflect the design intent. It's no good operating maintaining plants as independently from design. The design is only good if the conditions are maintained as per the design premise. That's a real important part of mitigation of Waterhammer. It's to understand the design and to make sure operating and maintenance practices reflect that design intent. The next few slides are going to run through some ideas, some thoughts, some general good practices for avoiding and mitigating Waterhammer. There's lots more. There's lots that can be done. I'm going to run through kind of the main points, but there's a lot of detail behind this. I'm just going to sort of summarize it really. Otherwise, we'll be here forever talking through the minor points. But steam flow driven Waterhammer, as I mentioned, that's mainly on steam distribution pipework. So the key here is all about trying to avoid the accumulation of condensate within the system, either over the whole system or also in local pockets as well. Remembering that it can be, you can get Waterhammer by slugs being picked up out of low points pockets and pushed on. So everything here is about avoiding condensate accumulation. So it's about having slopes in direction of flow. So condensate will drain down to a sort of carefully managed selected low point. That low point has got the correct capacity, the correct facilities for capturing that condensate that drains down to it and then removing it. So that steam trap capacity, the spacing of steam traps, but making sure, of course, that the capacity is not just good for normal operating, it's also good for startup and shutdown scenarios as well. It's also really important to have the correct type of trap for the service conditions. So whether if the steam's superheated or saturated, you may need to have different types of trap to operate properly, and the wrong one may not work as wanted, or it may fail too frequently. So it's really key to get the right type of trap for the right conditions. And of course, once you've got the proper system design and the proper equipment in there that will work properly, it's important to regularly check and maintain these equipment items to make sure that they do function and they're not failing, either through sort of manual monitoring, but there's also a possibility of having automated instrumentation monitoring on steam traps to make sure that they are functioning and to raise an alarm if they go cold or there's no sound of them functioning properly, to then alert an operator or a maintenance person to go out and check the trap and to make sure condensate's not building up. And of course, steam systems need to be insulated. And again, this comes back to the design, the capacity for steam trapping. It will be designed allowing for insulation, and that insulation quality is to degrade over time, and the cladding that keeps it sort of waterproof, stops water getting in, rainwater getting in. Again, that could increase the condensate loads, which could exceed the design parameters for the trapping. So it's important to keep maintenance of insulation and cladding up to date as well. On the condensate collection and return pipework, the premise here to avoid it is a little bit different. So here we have to generally accept that there will be steam, flash steam, and condensate throughout the system. So it's a case of making sure that that's allowed for properly in the design. and it's allowed for properly in operating practices as well. So the key here is knowing where you think it could be two-phase flow. So making sure that's identified on P&IDs to make sure that operators are aware where two-phase flow may be occurring, but also to make sure that the appropriate piping design is put in place in terms of strength support, stress calculations to make sure it's strong enough to withstand two-phase flow. And the other point then is that to make sure the lines are properly sized for two-phase flow. So there can be many different regimes of two-phase flow, like stratified, annular, in trains, and they are relatively safe. You don't get sort of slugs and waterhammer occurring in those. What we want to avoid is the conditions and the velocities that lead to the wavy or the slug flow regimes, and that's done primarily if you get the right size, increasing the line size to slow down velocities so you don't get the waves or slugs forming. But two-phase flow in general, I think, is a good practice is to try and minimize where you have two-phase flow, because it does require additional support. There's always a risk of waterhammer with two-phase flow and other issues. And also you get much higher pressure drops in two-phase flow systems. So good practice is to minimize the extent of the two-phase flow piping. So by having local condensate collection and separation of flash steam, and then where possible, to maintain condensate streams well above their saturation pressure, particularly for long transfer distances. So when you're transferring it back to the power steam generation system, for example, or to wastewater treatment, maintain it well above saturation pressure, so there's no risk of flash steam occurring, and then some of the problems with two-phase flow that result from that. So avoiding waterhammer for the condensation-induced mechanism. All the methods or the avoidance mitigation steps I mentioned for the steam flow induced waterhammer are also applicable to this. But in addition, it's also about, I think there's a bit more in terms of system design to avoid condensation induced, to try and really sort of avoid mixing steam and condensate in the same lines, and to really then separate and have independent routing for vapor and liquid streams. So that's one element that's shown. The other is really minimizing the potential for steam breakthrough from control valves or steam traps, for example. So I talked about that's partly careful selection of the control schemes, careful selection of the steam trap type to make sure it's suitable, and trying to avoid continuous flow steam traps in certain situations, for example, where there is the potential for low condensate loads at one point, where you have the risk on a continuous flow device of steam breakthrough, and there's not enough condensate to plug the orifice. So all those kind of things need careful consideration. And it's a wider system design really is what's needed for condensation induced to mitigate that. There's proper employment of steam traps, flash vessels, let down of condensate, separation of flash vapor to route so the condensate and the steam in separate headers. And condensate-induced waterhammer, as I said, is a particular issue during startup and other abnormal loads when the system is not at its normal operating conditions. It's quite often really hard to envisage these and make sure they're designed out properly. So it's key during the design process and any subsequent HAZOPs, for example, that happen on the plant periodically, to get operations, to get maintenance input into that. So it's not just normal operation that's considered, and therefore to provide the equipment and the methods needed to manage these abnormal operations properly. And when you're not just relying on the normal control, normal equipment, which may not be suitable for these abnormal conditions and may lead to unsafe conditions. And a couple of examples of this would be, say, steam heat exchangers, where at turn down or at startup, there's a much lower condensing pressure inside the heat exchanger, and it's quite easy to flood the heat exchanger with subcooled condensate. And then if you put live steam on there, you're introducing live steam into a subcooled system. You haven't got the pressure to push the condensate out into the return header, so you can quite easily accumulate quite a lot of condensate and then inject steam straight into it, which can cause localized waterhammer. Another example would be, as I showed in the slide earlier, where you've got high pockets in pipework when they shut down. So you need to provide facilities to vent high points during startup, and or the ability perhaps to slowly pressurize lines to collapse those vapor pockets in a controlled manner before you then can start running normally. So there's quite a lot of sort of planning and foresight that needs to go into properly identifying where condensation-induced waterhammer could be a problem, and then really trying to design this out. So the last slide then on the topic of hydraulic shock and surge, how to avoid that. As I said, it's quite a different mechanism and potentially I would say the most serious in terms of Waterhammer causes. And this really is something that needs to be really looked at in a design point of view. It's very much down to the equipment that's used, the design for the system. There's little perhaps that operating practices can do about it. So the key here really is to know where it can happen and then to do screening, surge screening, and some pipework analysis to identify if peak pressures can be acceptable or not. If it's particularly high risk or particularly complex situation, dynamic simulation can be utilized. With software like FlowMaster, it can be done in HYSYS, where you model the pipework, the piping network or the pipework line, and then do a sort of dynamic simulation, transient simulation to look at what happens in preset scenarios and measure the peak forces it generated. But that can be quite time consuming and costly. So there are some good practices that looked at where you look at the length of the line, the density of the liquid, the velocity of the liquid, to work out whether potentially there is a sort of significant or potential surge situation. That's the screening phase, and then you can only take forward the high risk areas to dynamic simulation. That's a sort of standard approach which is typically followed. The mitigation steps can be, there's a number of them, and it may take one or all of these to safely mitigate the scenario, but increasing the line size may help by reducing fluid velocities. Definitely breaking the long transferred lines down into smaller separate stages would help, but then this obviously could require intermediate pumping stations, for example. The use of slow closing valves is a really big one. So anything that slows down the rate of change of velocity of the fluid will really help. So it's avoiding the use of quarter turn valves. I think all operators know that it's good practice not to close any valve as quick as you can, but rather just to slowly move it. But obviously something like a gate valve could take a lot of turns to close and is therefore by nature quite slow. A quarter turn ball valve can be shut very quickly, so it's best to avoid those in situations. And similarly for automated valves as well. Not to use quarter turn ball valves for on-off valves, air actuated or electric driven valves. And again, the valve trim can also make a difference as well. So use of equal percentage valve trims as opposed to any others where you do get that faster sort of closing section of the valve. Buffer vessels can be used normally kind of as a last resort, I suppose. So these are sort of partially filled vessels that would sit above the line with a vapor section in them, and the idea is that when you get that pressure wave, it's absorbed by compressing that vapor in the vessel as the vessel fills with liquid to take out that, or to buffer, to dampen that peak pressure. And then the last one, I guess, is probably the first one to look at, making sure you've got the pressure rating for the pipework. So it goes without saying that designing pipework, you need to make sure the design pressure is suitable for all scenarios where possible. And if long pipework, you need to consider these transient startup, shutdown, stop and flow situations. You need to have the pressure containment to support that. But on the other hand, if the peak pressures are really extreme, then that's not practical, and you need to do other measures to reduce that peak pressure such that the pressure rating can be accommodated. And of course, it's not just the pipework pressure rating, it's also the support that needs to go with that as well. Okay, so that was my last slide. Thanks very much for your attention. I know it's a fairly quick run through of a topic which many papers have been written on, many academic studies, and lots of site experience and documents have written on as well. So put some contacts on the screen here. So please don't hesitate to contact any of us if you do want some further information or further support in the future. Always happy to help. But I think we're probably gonna have time for some questions now as well. So we can run through those, see if I can address any points of interest for you. Thank you.
Hey, thank you, James. Thank you for sharing with us your knowledge and experience in this topic. Just before I open the floor for question, I have a couple of questions that can get it during your presentation. Under hydraulic shock, okay, in your presentation, you mentioned that the longer the length of piping is, the greater the peak pressure generated. How long is long?
So I said typically we're looking at sort of the long transfer lines, so hundreds of meters upwards, and that's twofold. One reason is that, as I said, the greater than the sort of the kinetic energy contained in the liquid column, the greater there is to generate these peak pressures in the fluid. So if you have a column of liquid in a line that's a few hundred meters long, that's got a lot of energy contained in there that you suddenly stop. The other thing is to do with then the actual fluid dynamics. As I mentioned, the pressure wave will have a certain wavelength, a certain frequency to it, and if the pipeline length is longer than that wave frequency, you can generate much higher peak pressures. If the pipeline length is less than that wave frequency, the wavelength, the peak pressures you can generate are not so high, so it's less of a risk. So that's the first thing we look at in the screening is really whether it's above that frequency, that wavelength. So you're typically looking at a few hundred meters or greater to be serious risk of hydraulic shock, surge, water hammer.
My second question is about analyzing the risk of water hammering for the Spirax system. Is there any recommended software?
Yeah, as I said, dynamic simulation package is what would be needed. So HYSYS has that capability in it to do that. Flowmaster is one that I typically used to use a lot in my previous company, Postawheeler, to do these studies. Pro2 will also have that, and I think other like Olga has potential to do that as well. It's really any dynamic simulation software, but like Flowmaster is probably more specialized in that area, whereas HYSYS is obviously a general process simulator. So we used to use Flowmaster.
Okay, and my last question, which is I would like just to know, in the good way is to reduce the water hammering. Is it, can we just count replacing the steam trap with a good one? That can be a good solution, or an easy solution. So
I mean, it depends on what the cause is. So hence when I started off saying that the water hammer, the knocking, the banging noise, the movement of pipework is a symptom rather than the cause itself. And then similarly going on from there, even if the cause is determined to be accumulation of condensate in the system, it may not be the steam trap that's to blame. It could be that the pipework supports have sagged slightly over time, so you've created a low pocket where there wasn't a low pocket by design. So there isn't a steam trap to remove from that bit. It could be that insulation is not doing its job, and therefore ambient losses are much greater, which is causing excessive condensation in the line. So there are other ways for condensate to accumulate in the system, not just the steam trap. It could also be that the steam trap is not fit for purpose for that that service, that scenario, as I said. So although replacing the steam trap in that situation would be beneficial, you need to make sure that it's not just a straightforward like for like, because that trap has just failed. It's understanding why it's failed. And of course, steam traps are not just installed on their own in a line. There's often isolation valves, strainers in there as well. So it could be a blockage of the strainer because of steam quality, condition of pipework. It could be that other valves have failed, stems have failed in the valve. So it's important to do a wider survey of, first of all, understand what's causing the water hammer, and then a wider survey of how it's occurring, why it's occurring, and what the causes are, rather than just going out and replacing a steam trap and expecting that to fix it, because it may not.
Okay, thank you, James. And now I would like to open the floor to our SMEs and the audience. If they have any question, just either to raise their hands or type it. Yeah, we have here Mr. Majid Abdallah. Yes, please, Majid.
Well, thanks, James, for your, very informative, fruitful, neat presentation, especially related to refinery, where we have many steam lines, many condensate lines running sometimes some areas more than 1 kilometer in distance. You are reminding me with an accident happened about 34 years back here in Buffalo refinery, that one of the steam line was low pressure line. and it wasn't given enough warming up initially. So just imagine we have that much of length in steam line, even if it is a low pressure, and you don't give it enough warming up, and it requires at least sometimes 8 hours, 10 hours, 12 hours. It depends to the size of the pipe and the length of the header itself. So when we placed it in service, unfortunately at that time, the line moved, and the drain line, one of the drain line, bent badly and hit the shoe, which is all made of carbon steel, just because of the absence of enough warming up. So that's one of the other causes that could cause bad hammering, water hammering, if not given enough warming up. Maybe this is good also for you, for your presentation. I mean, you mentioned this, but it was in implicit way, but not was very explicit. Maybe for the sake for the participant, this story could be beneficial for all. Thank you very much indeed.
James, this is regarding the condensate lines hammering. So when compared to the steam lines, condensate lines hammering appear to be like steam hammering. At least they add some more traps, or looks a little simpler than even this condensate line hammering. So what? How do you differentiate here in the providing the solution for condensate line hammering, condensate return lines?
Yes.
In terms of sloping and the number of breaks, or line length.
Yeah, so condensate line, it's really about understanding that where there is two-phase flow, it has to be by design. So it's not a case of trying to avoid, the liquid accumulation as it is in the steam system. The condensate, it's knowing where there's two-phase flow and then making sure the pipework is designed accordingly to make sure that it is the right size to keep you within a slug flow regime. Sorry, avoid the slug flow regime and the wave flow regime. So that's part of sizing, and to make sure that the pipework is anchored. The piping engineers know that there will be two-phase flow in that line, and to make sure it's more supported. The supports are stronger to deal with that. So there's some areas that you can't avoid two-phase flow. It's making sure that's known and designed. And then I think, as I said, it's good practice, I think, to just minimize the amount of two-phase or the length of two-phase line in practice. So having separation facilities as close to the source as possible, and then you can have your single-phase streams from there. And then where possible, to keep condensate lines, particularly where transferring over distance, single-phase at all times. So making sure that you have sufficient head-on pumps to keep the pressure well above the flash point. Avoiding high point elevation for condensate lines, where obviously at the high point you risk having it will be a low pressure, so you risk having breakout there. So I think that's, or you have a back pressure control valve at the far end to make sure that it can't drop below below the pressure where flushing starts to happen. So that's really the key to condensate systems. It's recognizing this potential is there and designing accordingly, and recognizing the two-phase flow.
I mean, the pumping pressure normally, the higher the better, you mean to say, is it?
Well, just to make sure it's above its saturation pressure.
Okay.
So especially on long transfer lines, you've got to account for the pressure drop. You've just got to make sure, taking into account elevation changes and everything else, that you don't get flashing and flaring. And obviously, as I said, at startup and shutdown, it's particularly important. You have to recognise that when the pump's not running, you're likely to have vapor pockets at a high point. And then when you start, you don't just start the pump and let all those vapor pockets suddenly collapse. You put in place either methods to vent down those high points, or to slowly pressurize those high point pockets to allow for controlled vapor vapor collapse, if you like, those high points.
Okay, thank you, James.
Any idea for this is question for James? Because when this water hammering thing plays, because I experienced this myself, and I lived with this in the 80s, and I know what the hammering is. We faced it in real life. It's really very scary. The noise is so big. Sometimes the noise is like a big bang. Any idea if this dB sometimes the noise level, is it measured? And do you have any idea about this, or any tried, or what? Can you just shed more light on the decibels of this noise of the when hammering phenomena taking place?
I don't think there are any particular noise. It can range from very minor, so you can just hear it, to extremely loud. I mean, I don't know what the peak decibels could be, but it's possible to rupture very high pressure steam lines if Waterhammer is severe enough, and obviously the noise from that would be extremely high. And the noise varies as well. So you get that sort of banging noise I think you're referring to, which is more of the sort of the steam flow, where you get those slugs of liquid hitting bends and corners. The condensate induced tends to be a much higher frequency cracking noise, almost sort of like a gunshot. It can sound a bit like that reverberates through the pipework in the metal, which again can be very loud, and from a hearing, from a safety perspective, I guess with the high frequencies can be quite damaging for hearing. But I'm not sure on actual decibel levels. It can be anything and everything really, depending on how severe the Waterhammer is.
Thank you,
James. How can steam distribution be made to maximize reliability and safety?
now James, charge Monif. He's more questions. Now you need to charge him.
Okay, spoken like a true EPC contractor. So, I mean, in terms of designing steam systems to maximize reliability and safety, there's lots of good design practices out there, from different operators, different EPC contractors, and also design codes, as the API. And these have been developed, from many years of experience and lessons learned. And really, they're all encompassing all aspects of the steam system, from the piping design, the layouts, the mechanical design as well, the process sizing and selection, even setting the process conditions you need, and then obviously the design of the steam trapping and condensate draining equipment. But as I said before, I think probably the key thing really for me is ensuring that any plant system, and this is not limited to steam and condensate, but to ensure that any plant system operates safely and reliably, is to understand all of the different operating modes and ranges. So not just the normal operating, starter, catalyst run, inlet catalyst run, for example, but the startup, the shutdown, any other intermittent abnormal operating modes, like the warming up of the steam header that we talked about before. Make sure all of those are captured and considered in the design, and there's appropriate facilities to deal with those. And then once you've got that design, the real key bit for me is making sure that design is imparted onto the operating team. So the operating team know how it's intended to operate, or to do this startup shutdown activity, and they know what facilities should be used to do it safely. And then you don't get that gap with operators trying to do things as best they think, but not really understanding the fundamental of how the system was designed, perhaps. And then that gap is where these events tend to happen. So the real key is understand the design intent that covers all operating ranges, and then maintain and operate the plant in line with that design intent.
Hey, thank you. Thank you very much for sharing. And just before we close, I would like to call Mr. Raj for his closing remarks.
Thank you, Munif. Thank you, James. It was a wonderful discussion and quite a good overview of this whole topic of water hammering. And it's interesting to note that it can happen in domestic atmosphere also, at home also. So we need to be careful about that. So do you have any tips for that?
No, just nope. Just tap off slowly if you want to avoid it. But
so don't close the tap too soon.
Yes, just nice and slowly.
Nice and slow. That's good. That's good. So thank you once again, all of you, all our subject matter experts, and also the Spirax people who kindly organized this with James. And if you have been following GDA Conversations, this is the 19th episode. And if you have not seen any of our, episodes, please go to our website. There you will find all the previous episodes with different industry leaders, very deep discussions with our subject matter experts. And I'm sure just like this session, you would get a lot of takeaways, useful and practical takeaways from these sessions. And with this, I would like to again thank you. If you have any question which you could not ask in this session, you could always send it to us at info@gda.org.ph, and we'll ensure to get you the answer from James. And if you have any other suggestions, please do write to us. And in the meantime, I wish you a very good health, safe, and prosperous future. God bless.